Sir, good evening, sir.
Good evening, Jaiprakash. So, Jaiprakash will start just after 5 minutes. People are joining.
Yes, sir. Yes, sir. No issues.
நான் அப்பெல்லாம் வாங்க போறது சாப்பாடு என்னன்னு சொல்லிட்டு இருக்கேன் நான்
Okay, good evening to all participants. Welcome back to the that is fifth day of the ATAL FDP program on Future Intelligent Network towards 6C. So today's speaker is Dr. Allam Jayaprakash. Jayaprakash, please can you check if you can see your
Yes, sir. Yes, yes. Sir, can I share my screen, sir?
yeah, you can say that. We'll just test it, then I will introduce.
Yes, sir. Yes, sir. Sir, is it visible?
Yes.
Yes, yes.
Okay.
Sir.
Good evening to all. So briefly, I will introduce Dr. Jayaprakash. He is a currently research scientist at the United Arab Emirates University, Al Ain, UAE. He works in the Department of Electrical and Communication Engineering. He completed his PhD from National Institute of Technology, Rourkela, specializing in artificial intelligence for biomedical signal processing, particularly ECG beat classification and healthcare analytics. He holds MTech in digital electronics and communication system from JNTU. And Dr. Prakash has made a significant contribution to the cutting edge research in deep learning, edge AI, ECG based decision support system, automated biomedical diagnosis, and healthcare IoT. His work includes advanced ECG beat classification architecture, multimodal biomedical signal analysis, explainable AI, hardware optimized learning models for real time deployment. Uh, he has published more than 30 peer-reviewed journal papers in leading SCI and Scopus indexed venues, including IEEE Transactions on Artificial Intelligence, IEEE Journal of Biomedical and Health Informatics, Frontiers in Digital Health, Engineering Application of Artificial Intelligence and Biomedical Signal Processing. He has also contributed several book chapters, delivered invited expert talks in different venues like NIT, Jamshedpur, Vellore, and UAE University. And he's served as the editor in the SAGE and MDPI artificial intelligence and acted reviewer in top journals like IEEE Sensors, ASSES, IEEE ASSES, and expert system with application. And he is the recipient of the Stanford Top 2% Scientist Recognition 2024 and holds the multiple patent granted in AI-driven healthcare system assisted technology from UK. His professional experience spans a role as a senior assistant professor at VIT Vellore, senior research fellow at NIT Rourkela, consultant for MEDTL, CIFRS, and developer of machine learning algorithm for medical application. So we are honored to have him today with us. I welcome Dr. Jayaprakash, and please take over the eyes and deliver your lecture.
Thank you. Thank you, sir. Yes, sir. I'll start it, sir.
Yeah.
Very good evening to one and all. Today, I want to give a lecture on applications of artificial intelligence and deep learning in next generation wireless communication, especially in the modern wireless communication. What is the role of deep learning and how it is effectively working to accommodate existing problems and all I'll discuss. So this is my major title and these are my outlines, very simple outlines. I'll give a small introduction regarding your communication systems And after that, basics of AI and deep learning. AI for spectrum management, especially spectrum management is very important in communication, as you already know that. Why? Because you are all people expert in communication. So spectrum management is very important. And fourth one is security and privacy enhancements, and how to increase the security and privacy enhancement in the networks using deep learning. I'll discuss. And after that, AI for IoT and edge devices, especially after preparation of the deep learning algorithms, if you want to dump or if you want to deploy the algorithms on any local devices, then how to deploy those algorithms on edge devices like Arduino and various STM32 microcontrollers you have. So how to deploy and what kind of challenges we'll face during the deployment and all I'll discuss. Well, because currently I'm working on deployment of deep learning algorithms on edge devices only. Currently I'm working. So after that, I'll give you the little future directions and research opportunities in this particular area. And finally, I'll conclude my topic with my conclusions. And as you are already aware about evolution of wireless communication systems, this particular figure illustrates the historical evolution of wireless communication technologies from 1G to 6G, showing how each generation introduced major advancements in capability, speed, and connectivity. Especially 1G, first generation systems are analog based as you already aware. And this is basic mobile calling application only we have, but the mobile phone's size is huge and low capacity and low security even. And after that, coming to the second generation phones, second generation technologies, communication, wireless communication, we have like GSMs and CDMAs based on digital voices. So we have some better voice quality and we have SMS messaging option and improved security compared to the 1G. 1G is like better than, I think, at least it's wireless and mobile. That is the first generation, but voice quality is very bad in first generation. And after that, coming to the 3G, in third generation, they introduced mobile data plus internet access, both enabled mobile-based web browsing. So email and early apps we have. The speed of the internet is like hundreds of kbps to a few mbps. And after that, in the fourth generation, smooth video streaming started and online gaming is also introduced and faster downloads we experienced. So high speed mobile broadband we introduced in fourth generation communication systems, and speed is also like tens of mbps to hundreds of mbps. And after that, 5G, coming to the fifth generation, we have fast broadband. It is around 2020s it started. So very high speed and very low latency. The speed of the network is very high. So which supports IoT devices, smart vehicles, real-time applications. The speed of the network is up to multiple gigabits per second. And after that, we have now sixth generation. In this sixth generation, this is like intelligent connectivity everywhere. So AI-driven based communication. Like we can connect the drone network, smart cities, holographic communication, like real-time 3D communication, and satellite networks, and all are comes with the 6G connectivity. So this particular figure shows the how wireless communication has progressed from simple voice transmission 1G, 2G to mobile internet 3G to high-speed broadband 4G, 5G, and now moving toward intelligent everywhere available connectivity 6G. So this is the particular evolution of your wireless communication. You already people aware much more than me. And why AI is now essential in modern communication networks. Like now 6G networks are there. Like in this particular 6G network, 6G wireless communication, why we want to introduce artificial intelligence. The first important point is increasing network complexity. Now almost in 4G, 5G, 6G, the network complexity is very huge, very huge. So to handle that complexity manually is little bit impossible, and with traditional algorithms are also it's huge burden on traditional algorithms. So we need to manage this complexity in an intelligent way. So to manage this complexity, we want to include artificial intelligence in the networks. And the second one is huge data availability. Nowadays, we have huge data. Huge data is burden aside, but for the but coming to the artificial intelligence networks, when you have more data, deep learning algorithms we can train in a better way for getting better results. So when you have less data, algorithm training is very difficult, but when you have more data, algorithm can train in a better way and you will get better results also. So as we already have huge data in these networks, so algorithm training is very easy, and managing automatic things are also becomes very easy if you will incorporate artificial intelligence in the networks, AI. And especially another thing is like non-linear and unpredictable wireless environments. As you people already know that wireless environments are unpredictable and it is non-linear, but non-linear modeling is very good in deep learning models. It is excellent at capturing non-linear relationships. And after that, reduction of computational complexity. So we can do offline training and fast inference, real-time capable also AI algorithms will do. When you will do offline training, like offline training will take more time, but after complete proper training, if you will apply any input data to the algorithm, you will get output instantly. So that is the more advantage in deep learning algorithms compared to the traditional optimization techniques. And after that, whereas if you consider the 6G networks, you have different applications like self-learning network, zero touch, intelligent reflecting surfaces, semantic communication, and different AI native radios, base stations. So you have different 6G applications where you need real-time and real-time interference. So at that time, you need AI applications to handle such kind of networks. And after that, these are the unlocking new applications. As we are already aware about autonomous vehicles, remote surgery, smart city, especially in biomedical applications. Now remote surgeries also came. Why? Because in the remote area, maybe all the doctors are not available. So we can operate surgery from the long distances to the remote areas. This will be possible when the network speed is very high and efficient, and we need to take decisions also rapidly. And after that, it will accommodate another thing is also like digital twin for 5G and 6G communications. That means we have physical network somewhere. The same physical network will replicate in our laboratory, and will update this particular network with the data, with the physical network data. That means the real world data will use to train the replica of the replica of the real network. That's why this is called as digital twin. That means this is kind of a feedback loop. Continuously the algorithm will train, and the algorithm will update the weights and biases as per the real-time data to get the better results. And what are the main key challenges in wireless communication systems? What are the exactly, as you already people know that what are the exact challenges in the wireless communication? First one is spectrum scarcity. As you already know that the radio frequency spectrum is very limited, but the number of wireless devices are increasing, like phones, IoT sensors, vehicles keeps increasing. So as demand grows, there is not enough clean unused spectrum to support high data rate communications. This leads to congestion and reduced performance. So to handle this congestion effectively, we need some intelligent techniques. Okay. And second one is latency. Latency is nothing but it is delay between sending and receiving data. In modern applications like AR and VR, autonomous driving, real-time control, and cloud gaming require ultra low latency. That means we need very less delay to transmit the data from transmitter to receiver. And network congestion, long routing paths, and limited processing power often increasing delay in these networks. And third one is mobility. Devices in motion. When the devices are in motions like vehicles, drones, mobile users cause rapid changes in signal quality. So the network must constantly track moving devices, perform handovers, and maintain connection stability. We need to maintain connection stability. That is also important. So high mobility makes it harder to deliver consistent quality of service. So this is also a biggest challenge. And last one is interference. Wireless signals share the air, as we know. So they often interfere with each other. This interference can come from other wireless users or nearby devices or overlapping channels. Severe interference reduces data rates and increasing error rates. So modern wireless system must handle limited spectrum, real-time communication demands, high mobility and signal interference, all while supporting billions of connected devices. So these are the key challenges in modern wireless systems. So now I'll introduce artificial intelligence, different artificial intelligence techniques, what we have in machine learning and deep learning, I'll introduce. Coming to the artificial intelligence, artificial is nothing but man-made and intelligence is nothing but ability of thinking. Mainly, what is the difference between humans and machines? Machines cannot think and humans can think. How we are able to think? Like from our experiences, we learn something. Because of that, based on that experiences, we'll do the actions. So in the same way, when you are able to give these experiences to machine also can mimic the humans. So that is called as artificial intelligence. Okay. Then why artificial intelligence came into the existence? Before coming to the artificial intelligence, we have different kinds of techniques like rule-based techniques and template-based techniques we have. Rule-based techniques means we have some if else conditions and while conditions and switch conditions and etc. But every problem has multiple number of conditions, like many conditions we have. So we can't incorporate all the conditions to get the better results. So rule-based algorithms ruled out by using template based. That means we'll use some standard templates to match the existing data with the existing data to take the decisions. But that is also very difficult. Why? Because in real time we may get any template, so that template may not exist as you have. So template based method also ruled out. So after that, machine learning algorithms came into the existence. What machine learning algorithms will do, will extract a unique significant features from the data, and those features will use to train the algorithms. Like fully connected network will pass these features, important features, to train the algorithm to get the results. Like you see, if you have A and B person, you need to extract a unique significant features from these two persons to differentiate those two people. Like what is the DNA of that person, what is the blood group of that person, what is the son of that person, mother of the person, where from where that person comes. So this kind of some unique features, unique significant features you need to identify from the data. So when you are able to extract unique and significant features from the data, then it is very easy to train the algorithm to get the better results. So that all the machine learning algorithms efficiency is completely dependent on the quality of the features. If you are able to extract the quality features, then your accuracy or performance of the system is good. If you are unable to extract the unique significant features, then your performance of the algorithm will drastically decrease. So the algorithm's performance is completely depending on the features. So later on, what researchers thought, maybe if you are very good at those algorithms, like in digital signal processing algorithms, so you can extract the good features from the time domain data or images or whatever it may be. Maximum communication will handle with time domain data. So we need to use a very good digital signal processing techniques to extract the features if you are able to use machine learning algorithms. If you want to use machine learning algorithms, you need to use a better time frequency transforms to get the features. But implementation of these DSP algorithms are very difficult. Why? Because everyone may not expert in that particular area. So that what researchers thought, we need to develop an algorithm to extract features automatically from the data. So that convolution neural networks came into the existence. In convolution neural network, what we'll do, we'll extract the features automatically from the input data. There is no necessity of any DSP techniques to extract handcrafted features. There is no necessity of any handcrafted features. Deep learning algorithms can extract features automatically, and classification also it will give automatically. There is no much difference between machine learning and deep learning. The only difference is initial convolution layers. We have initially convolution layers plus fully connected network is nothing but deep learning algorithms. So deep learning algorithms. Here, another difference is also like in machine learning algorithms, if you have very less data also, you can manage. Somehow you can manage, but if you have less data, training of deep learning algorithms is very difficult. So in this particular diagram, if you will see, artificial intelligence is the universal data set. In this universal data set, machine learning, deep learning, computer vision, natural language processing, and data science, everything comes under the artificial intelligence. The differentiation of these like sub things like machine learning, computer vision, deep learning, that depends upon your algorithm. If you will utilize machine learning algorithm like feature extraction plus some support vector machine or random forest or some KNN or whatever it may be, if you will use that, comes under to the machine learning. If you are using convolution neural network, long short term LSTMs or by LSTMs or by grooves or something LXNet, if you will use, then that comes under the deep learning algorithms. And computer vision is nothing but when you want to process any digital images and videos, then you need to go for computer vision. And natural language processing is nothing but nowadays whatever we are using, chat GPT, generative pre-trained transformers. These things will work based on natural language processing. That means we'll process the text and we'll understand the text, and after that we'll give reply accordingly. Machines will give reply accordingly. Nowadays in communication also, in latest 6G communication also, they want to incorporate natural language processing systems. Why? Because instead of transferring the entire data, if you are able to transmit the gist of the information, then you can reduce the amount of the data which you want to transmit, and the information will reach to the receiver end. So that nowadays NLP techniques are also, they want to incorporate in 6G. And after that, data science. Data science is not exactly a subset of machine learning and AI, but it uses an DL to gain some insights. When you want to get some insights from the data, then you need to use data science. So that is the major advantage of data science. So these are the major differences between the artificial intelligence, machine learning, deep learning, computer vision, data science, and NLP. And after that, what is computer vision? These are the major differences. Computer vision, it helps systems understand and interpret the visual world in the way humans do. Generally, whatever the image we'll consider, that image is image for us, but that is digital input for the system. So we want to process those images through different computer vision techniques. And after that, in machine learning, as I already said, that it provides machines the ability to automatically learn and improve from their past experiences. Deep learning is also same, as it is also a subset of AI. So the idea is to mimic how the human eye can capture light and color in the real world and extract information from images. In the same way, by using computer vision also, we'll extract the information, meaningful information from the images and videos. And these are the major differences between deep learning and machine learning, especially the data requirement. The data requirement is very high in deep learning. The data requirement is not that much high as like deep learning in machine learning. But here whether if you have any problem, whether you want to choose deep learning algorithm or machine learning algorithm, how will choose? That completely depends upon the availability of the data. If you have more data to train the algorithm, then you can go for deep learning. But if you have less number of data, in a less quantity of data, if you have, then you can go for machine learning algorithm also. There is no problem like nowadays deep learning is the only booming, so we have to use deep learning. So there is no such kind of rule to use deep learning and machine learning algorithms. It depends upon the application and the availability of your data and the accuracy. Especially in the deep learning, we have higher accuracies compared to the machine learning. Why? Because the depth of the network is very high in the deep learning algorithms. But the training time of the deep learning algorithms are very high. The training, sometimes it may take days and weeks, couple of weeks also it will take. And in machine learning, it won't take that much time, maybe a few hours to few seconds also we can complete machine learning algorithms. Why? Because almost majority of the information, majority of the features will extract in the initial stage of the algorithm manually, so that there is no much requirement to train the algorithm. And third one is hardware dependency. If you want to train the algorithm, machine learning algorithm, there is no requirement of GPU. So based on CPU also you can train the algorithm. But if you have GPU facility, then you can use machine learning algorithms also. But deep learning algorithm requires GPU to train properly. You have to, suppose if you have large number of data, then definitely you need to utilize GPUs in the deep learning. Okay. Uh, but testing time is very less. As I already said it in my previous slides, deep learning will take more time for the training, but for after completion of the training, the testing time is very less. The testing time is very less. And feature selection. There is no feature selection in deep learning. Why? Because it will automatically extract the features. No human intervention. Completely, there is no human intervention in extraction of features. But in machine learning, we need to extract features automatically. And same data interpretation is a little bit difficult. Some machine learning algorithm easy to interpret. Number of algorithms. We have very few algorithms in deep learning, but you have many algorithms in machine learning algorithm. Nowadays, actually, explainable artificial intelligence also came. In artificial intelligence, we can know that why that particular decision comes from the network. Like all the deep learning algorithms are the block boxes. That means why that particular decision is coming from the network, nobody knows. That's why actually in industry also, in industry and in biomedical application, majority of the industries are not adopting these algorithms. Why? Because these are block boxes. Why that particular algorithm is giving that decision, nobody knows. Because of that, all the deep learning algorithms are treated to be as a black boxes. But now some XAI algorithms came into the existence, so we'll know the reason behind the decision. We'll know the reason behind the decision. And if you want to start the deep learning, how to start? So first you need to go through the linear algebra and calculus, and after that statistics and probability also it is necessary, and the basics of some key machine learning concepts like what is overfitting and what is underfitting and what is perfect fitting, and some metrics like accuracy, sensitivity, specificity, positive predictivity. What are the metrics you have to measure your algorithm performance, and all those things you need to learn. And after that you have different programming languages. Mainly nowadays people are utilizing Python as the main source language to develop the deep learning algorithm. Suppose you can use MATLAB also. Suppose if you are not familiar with the uh, coding, then also there is a possibility to implement machine learning algorithms and deep learning algorithms. You have Waikato University developed one graphical user interface that is called as Weka. In that directly you can access the data. You have some icons, so you can drag and drop the icons. And another supporting is also there. You have that is Orange. In Orange also same way, you can drag and drop the algorithms, and you can connect different pre-processing techniques, different algorithms for getting output, and for proper training of the machine learning algorithms and deep learning algorithms. And in addition to that, you have RapidMiner. In recent days, RapidMiner is also a very good software to implement different machine learning and deep learning algorithms. It is free for the education, so you can use the educational version for your experimentation and everything. So RapidMiner, Weka, and Orange, these three are the GUI tools to implement the different machine learning and deep learning algorithms. And this is the end-to-end process. Suppose if you have some data, if you want to experimenting on some data, then what are the important stages you need to follow? First, you need to import the data set. Whatever the data set you have, first you need to import the data set. In that data set, what is your data and what is your target label you need to identify. Suppose some bandwidth allocation only you have. Suppose if any channel is free, then only you have to allocate some user to that particular channel. That means when the channel is free, then that is 1. And when channel is busy, suppose that is 0. Then that 1 and 0 are treated to be as a labels for your data. So first you need to identify labels and data from your data. Okay. And after that, if you have any anomalies, if you have any problems in your data, then first you need to pre-process the data. You need to pre-process cleaning and normalizing and all those things you need to do. And after that, you need to visualize the data. At least first once you need to visualize the data, whether the data is very clear or not, that you need to visualize. And after that, you need to design your own architecture. How many layers you want, what kind of layers you want, how many convolution layers, how many batch normalization. So whatever the layers you want, how many layers you want, that you need to create your own architecture. And after that, you need to train the model. You need to train the model. And after that, you need to evaluate, like you need to check the performance of the model. If your performance is not good, again, you need to repeat the process. Again, you need to tune the parameters of your model, to get the better results, So this is complete after completion of complete requirements. That means if you are able to get the proper accuracy of your model, then you can dump the model or then you can deploy the model on your edge devices for real world testing. Here, everybody, what they will do is like, if you will get suppose 99% of accuracy, then we'll finish the experiment and we'll say like we got good accuracy. But you need to check the cross validate 10-fold cross validation you have, or 5-fold cross validation you have. So one leave, one out you have. So different validation techniques you have. By using those validation techniques, you need to check whether your algorithm is perfectly fitted or not. Like if your training accuracy is very low compared to the validation accuracy, that means your network is underfitted. Your network is underfitted or overfitted, whatever it may be. So based always the validation accuracy should follow the training accuracy. Then only we'll treat it as your network is properly fitted with the data. So this is complete end-to-end deep learning process. So this is the thing. If you have original data set, then you can randomly split it like 80% you can use it for training and 20% you can use it for testing. As in your communication, you have large data sets, you can split the data set into 3 different parts. First one is training data set, and second one is validation data set, and final one is testing data set. So 3 parts you can use. Why? Because I experienced some communication data sets. As you have millions of database you have, so you can use you can use always 3 splits. That may be random split or perfect splitting. So what are the popular sources for deep learning data sets? These are the different sources: Kaggle and UCI machine learning depository, data sets via AWS. Nowadays, Google's data set search engine also came. So all data set sources I kept here. So you can use these data sets for your experimentation purpose. And after that, here you have one more doubt, like how many layers I need to keep, suppose always when you want more performance of your algorithm, you need to keep more number of layers. But when you will keep more number of layers in your algorithm, it will leads to the vanishing gradient problem. That means the important information from your data will vanish at the end of the layers. So keep on stacking layers is not the only solution to get the better accuracy. So at the time, what we need to do, we need to use some skip connections to bypass the gradient information from upper layers to the lower layers. That is called as residual connections or skip connections. Because of that, we have residual neural networks. That means when suppose if you are keep on stacking layer also, you are getting good accuracy. At that time, you need to use skip connections or bypass connections to bypass the gradient information from the upper layers to the lower layers. That is one kind of technique. And the second important thing is like we are all handling the time domain data, temporal data. That means we have more temporal variations. Why? Because these are all non-stationary data. So LSTMs are long short-term memory techniques, LSTM recurrent neural networks based on RNN. So LSTMs, bidirectional gated recurrent unit techniques are very useful to handle this kind of data, especially communication data. Why? Because when you want to capture long-term dependencies, convolution neural network, what it will do, convolution layers will extract or will take the decision based on the instant of time. But LSTMs are not like that. LSTMs will memorize some data up to some time period, up to some time period. So when you want to extract any temporal data from some time period means you need to go for LSTMs. If you want to more effective training, then you need to go for bi-LSTMs also. But bi-LSTMs are little complex and it has more number of parameters, and you can't dump such kind of bi-LSTMs on any edge devices, so that you can go for bi-GRUs also, bidirectional gated recurrent units also you can use to make your algorithm proper and effective. This already I stated, and this is like deep learning for spectrum management. How deep learning we can use it for spectrum management? Here I'll give you one example. I have already done one example. I'll show you. One second, I'm sharing screen. So this is one deep learning algorithm I developed for the just demo purpose, for just some demo purpose. Like here, spectrum occupancy, simple spectrum occupancy, where spectrum is free. At that time, we have to assign the spectrum. Like deep learning model that shows how AI can help with spectrum management by predicting which channel will be free in the next time step. I simulate four wireless channels here: channel 1, channel 2, and channel 3, based on deep learning only. Like here you see, this is the prediction. Whatever the blue line you have, that is prediction. Where the channel is free, then it is showing like you can maybe the channel is free for the for future, like that it will predict automatically. So one random data I generated here. These are the four channels: channel 0, channel 1, channel 2, channel 3, and different occupancies of those respective channels. And here simply I utilized two dense networks, and after that I trained the algorithm, and automatically it will predict the uh, freeness of that particular channel. So in the same way, just I extended this program for this, like just up to 3000 samples I took. So where the channel is free, it will automatically predict the next time channel will be free. So you can utilize like that. It will prediction. You can use for the prediction problems also. So we generate a synthetic spectrum with four channels. Each channel's occupancy, whether it is busy or free, changes over time in a complicated way, like real world traffic. For each channel, we look at the last 10 time steps, busy or idle history, and ask a neural network, will the channel be free in the next time step or not? We use a small fully connected neural network here. Pick a random channel. Sometimes it's free, sometimes not. Suppose if it is random policy, if you will consider. But in AI policy, if in AI algorithm, if you incorporated, for each channel, compute the probability it will be free and pick the one with the highest predicted. Like it will compute the prediction of the four channels where you have highest prediction for freeness. So that particular channel, it will shows to the user. You can use this one like that. So to the network. So generally, instead of assigning randomly, this will be the best technique to assigning. And this is the another problem. Just wait, I'll share my screen now. Sir, is it visible, my screen?
Yes, it is visible.
Yes. So these are the different results. And after that, security and privacy enhancement, like modern wireless networks face threats such as eavesdropping and spoofing, jamming, malware injected IoT devices, and data leakage. So AI and advanced communication techniques significantly improve security and privacy and trustworthiness. Here I consider three data sets like benign, DOS, and scan. So when I have this data with these three labels. So I trained the algorithm using these three labels, and finally the algorithm perfectly trained. Why? Because here the validation accuracy is properly followed the training accuracy, and this is the 2D PCA projection of test data, whether the data it is able to separate or segregate properly or not. Here you can see. And after that, what is AI for IoT and edge devices? After proper training, if you want to dump the algorithms on IoT devices, you have different IoT devices like Arduino devices. You have Arduino Nano BLE. You have different versions, and STM32 also. You have different series. Nowadays, most of the series are supporting deep learning algorithms. Edge AI means running AI models locally on devices rather than in the cloud. Why we want to run the deep learning algorithms locally? As you have more facilities in cloud. Suppose in cloud you have more security issues. Deep learning algorithm is nothing but finally the tuned weights and biases. Suppose if any hacker wants to change some weights and biases in the network, then the result or then the classification result or prediction result or regression result will be completely changed. So we have such kind of problems. But when you are using in sensitive applications like in military applications or in biomedical applications, always you need to go for the edge devices dumping. So this is essential when you need like low latency, offline operation, privacy, reduced bandwidth, low power consumption device when you have. So all these things needs offline processing using edge AI devices, edge IoT devices. And you see, as we have in communication also, we have many sensors and we have many sensor data. So IoT devices continuously send data such as sensor readings, device status, location and mobility, environmental conditions, user behavior. Why this helps in communication? Networks can use this data to optimize spectrum, power, routing, and scheduling. And after that, IoT devices provide the context of the environment also, whether a user is moving, whether a channel is congested, whether a link is blocked, whether interference is rising or not, like automatic decision, like completely we can dependent on the algorithm for taking decision and instantly. Why? Because we need a low latency devices always. So IoT devices are very important to take the decisions very fast and quickly. Here, Arduino Nano and STM32 MCUs are extremely helpful in IoT communication. They play a crucial role as edge devices, sensor nodes, gateways, and embedded intelligence units in modern AI-enabled communication systems. And why industry uses edge AI instead of cloud AI? As I already said that low latency, privacy, reduced bandwidth, reliability, energy efficient, and scalable also. So these are the main important things where industry is preferring edge AI instead of cloud AI. And these are the future directions and research opportunities. We have like how low can we go without killing task performance in noisy sensor environments, and how to do joint optimization and hardware algorithm co-design and event-driven TinyML, especially nowadays TinyML techniques are popular or became popular. So these are the future directions if you want to work. And these are my conclusions. Artificial intelligence and deep learning are transforming modern wireless communication, enabling smarter, adaptive, and data-driven networks. And second one is, as wireless systems grow in complexity, traditional handcrafted algorithms are no longer sufficient. As I already said that initially we have some algorithms like rule-based algorithms, template-based algorithms. Now those algorithms anymore won't work. So we need to go for advanced algorithms using deep learning and machine learning. And the AI-based spectrum management improves channel prediction. Definitely, AI-based spectrum management will improve the channel prediction, inference avoidance, and resource allocation. And security and privacy are significantly enhanced through AI power introduction, detection, anomaly detection, federative learning, and etc. And microcontrollers like Arduino Nano and STM32 act as a powerful edge nodes. 100% these Arduino Nano and STM32 will plays an important role in edge devices implementation. So finally, my conclusion is AI plays a very important role for effective using of resources in 6G or 5G technology. So these are my conclusions. Thank you. Thank you very much. The next continuous session will carried out by Dr. Hiramat sir.
Participants, if you have any questions to that is Dr. Jay Prakash, please you can ask.
Hello, good evening, sir. Sir, am I
Yes.
audible?
Yes, yes.
Thank you, sir. Very informative. Sir, I have one query for validation purpose. Actually, where we can get this 6G data?
What, ma'am?
For validation purpose, so where we can get this data, sir, for the 6G?
Ma'am, actually, I'm not expert in this communication, especially in this communication area. But you may search in Kaggle or Google datasets to get 6G data, ma'am. I think it is still maybe
Shall I
Hiramat sir
answer Dr. Jay Prakash?
Yes, sir.
Yes,
Yes, sir.
Ma'am, there is a one portal that is WCL, wireless communication portal. Machine learning for wireless communication portal that is we supported by IEEE ComSat. Usually you get there most of the data set. Also some of the universities, because still 6G is not deployed, that is only in the research level.
yes, sir.
So
Yes, sir.
you can refer NUI that is models to generate your own synthetic data set, or you can refer the that is ComSoc data portal, and there is a IEEE data portal also where you can get similar type of data set.
Sir, is it open source?
Yes, ma'am.
Okay, sir. Could you please send this website address actually in the chat box?
Okay. Once this my session was, then I will be sending it.
Okay, sir. Thank you, sir. Thank you so much. Thank you.
Good evening, sir. Am I audible, sir?
Yes, ma'am. Yes, ma'am.
Yes, sir. So you described that the role of AI and ML and deep learning in IoT. So
Yes.
for project purpose, while interfacing the sensor circuits, how it will be beneficial means how we can implement like this with the block diagram. You can just give me a briefing about it because I'm familiar with IoT separately. Like with controller, we can connect the sensor, and with deep
Yes.
learning and machine learning, how we can do so.
Ma'am, actually, first, Hiramat sir, sorry, I'm taking your time. You may have session, but I'll close it as soon as.
No problem. Okay, you can take.
Yes, sir. Ma'am, actually, first, what you need to do is you have many communication, like if you will consider some spectrum allocation problem, you have many databases in Kaggle, So first you need to train your algorithm on Python. Okay. That is first step. And after that, after complete proper training, you need to save the model in .h5 format. Okay, .header file format you need to save. And after that, you need to prune and quantize the model. And after that, you need to dump that quantized model on Arduino board. And after that, whatever sensor you want to connect in a real time, you can connect that sensor to the Arduino board to get the real time data to test the dumped algorithm. but that the data which you are transmitting from sensor, the data shape also should be same as like trained data. Okay, na ma'am? So nowadays, like nano BLE on edge device, especially nano BLE is supporting for the deep learning algorithms, ma'am. In STM32, F series and N series also supporting. So the same process. If you want to utilize STM boards, then you have some ST Edge device, ST Edge developer cloud. It belongs to the company of ST microcontrollers only. Whatever the model you want to train, after training, you need to upload to the cloud. So automatically they will do pruning, quantizing, and they will give the final model where you can dump that particular model on STM board directly. After that, you can interface whatever the sensor you want. Hello?
I
Hello?
think
I think she has some problems.
please suggest some suitable PhD research areas related to wireless sensing and next generation IoT applications.
Sir, you may suggest, sir.
Thank you, sir.
Okay. So once our this
Yes, sir.
completes, then I can suggest some, and they can
Yes.
refer. I have sent the link where they will get a recent topic related to wireless communication.
Yes, sir. Yes.
Research areas related to wireless communication in ComSoc. Best reading is the best resource.
But what I understood, sir, actually, I'm not the expert in communication, but there is huge chances of deploying different deep learning algorithms in this particular area, sir. As we already worked in that spoofing.
Yes,
We
yes.
already worked
There are
on
a lot
spoofing,
of
and this is very good area,
people
sir.
are applying. There are explainable AI model-driven approach. Recently, last 5 to 6 years, lot of research is going on by
Yes, sir.
applying deep learning.
Yes. Yes, sir. Especially quantum CNNs also they can deploy it, sir. I studied
Okay.
on that also. That is very interesting.
Okay.
Sir,
Thank
I am very
you.
sir, I am very grateful and thankful to you for giving such a great opportunity.
Yeah, it's a very nice and intuitive talk, and very fundamental in which it differentiated what is a machine learning, deep learning, how it can be applied, and very important thing is you could give the demo on that is the wireless application. That is a
Yes.
great thing, and very thankful to you, Jayaprakash.
Sir, thank you very much, sir. Thank you, sir.
So I
Thank you,
will
sir.
just share my screen.
Yes, sir. Yes. Thank you to all the participants also. Thank you for your cooperation.
So, good evening to all the participants. So, I would be taking the next lecture. That is, topic name is Deep Learning Based CSI Feedback Framework for Massive MIMO System. So, I am audible, I believe, right? I think
Yes,
my
sir.
screen is
Yes, sir. You are audible, sir. You are audible, sir.
Yeah. Thank you. This is the one of the my PhD student work, and her two, that is 3 works I am just presenting here. So CSI feedback, as day for yesterday, Professor Deshmukh and yesterday Professor Subra Das was telling, channel is the that is bread and butter of any communication engineer. So here we are discussing about channel state information feedback. Mainly when you see that channel is very important for modeling all our communication system. So when you consider, when the system becomes very complex, in that case, channel state information also would be very huge in size. So how to feed that huge, that is channel matrix, is a very difficult task. And whereas you know that UV would be usually when we use the FDD mode, where you need to where reciprocity principle doesn't apply. So in that case, UV has to bear the that matrix, and indirectly reduces the, that is what you call, efficiency of the system. So to work on that, usually some of the conventional approaches are used, and recently the deep learning approach has gained a very that is what you call importance because of its application in different areas. And also in wireless, it is widely nowadays tested for like modulation, classification, sensing, and then cognitive radio applications and so on. So that is a introduction. So as we see that 5G network form the technological backbone for next wave of industrial and economic and societal transformation. And 5G new radio is the global wireless standard, which is defined by 3GPP. And we know that it operates in extensive spectrum range, but presently most of the 5G which are deployed, it is in the sub 6 gigahertz band, but it can have in range from 30 to 300 gigahertz, which can enable the extremely high data rates, and ultra low latency is possible. So three primary service categories of 5G new radio, that is URLLC, that is ultra reliable low latency communication, and massive machine type communication, and enhanced mobile broadband. So which are used for different application, and based on that, these all three service can be used. So the key enabling technology for these include, that is massive MIMO, millimeter wave communication, and device to device connectivity, and ultra dense network, and cognitive radio and intelligent spectrum management. So these are the some of the technologies which are like massive MIMO, millimeter wave communication, device to device connectivity. These are ultra dense networks. Some are already considered, but cognitive radio, intelligence, spectrum management, it is considered to be part of 5G and beyond, and not fully in full form, but as a some assistance. So coming to CSI in massive MIMO system, first thing we should understand what is a CSI. So CSI is the that is what you see. It is a channel state information, which is a core foundation of any modern wireless communication. It tells the transmitter how the wireless channel behaves, and enables the smarter and more efficient communication strategies. So why the accurate CSI is essential for our modern communication, wireless communication? Mainly, it directly impacts the enhanced user performance, ensures that reliable and high quality communication and high data rates are possible, and manages the interference control, like helps the base stations suppress the interference and improve the network stability, and also efficient resource allocation. So it enables the intelligent scheduling and beamforming, and power control for massive MIMO system. So its relevance in 5G and beyond is very important, because we are dealing with a huge that is what you call users, as well as to accommodate a huge users, we are considering a massive MIMO system. So a success of massive MIMO system actually depends upon that is CSI acquisition and feedback strategies. So accurate CSI becomes even more critical as the network evolves towards the 6G, where the ultra dense deployment and new frequency band demand what is called precise channel knowledge to get into a what is called very reliable communication. And also we need to as we go for 5G and beyond, the applications are also that is are also enhancing in nature. So motivation for CSI feedback in massive memo is, so this is a typical diagram which shows for the case of FTD mode. So we know that we have two approaches. One is FTD mode approach and other is a TDD approach. So TDD approach is a fully digital in which we are expecting in future generation. But presently still we have a FDD mode. And still, if you go for TDD also, the CSI feedback is necessary. But here it is shown that typically we have a G node V and UV. So CSI reference signal, that is channel state information reference signal, is some kind of filet signal is sent from the base station to the UV. And here UV is able to, that is get the estimate the channel, and from there it is going to feedback to the, that is what you call base station. So usually the what it is going to feedback is it would be having a what it gets is first from the file. Usually it would be channel matrix, coding matrix indicator, channel quality indicator, rank indicators, okay, which are going as a sum of the what we call as numbers. Right. So from there you will see that UV would give that to the base station. From based on that, base station would decide what type of modulation I should send, what type of MIMO setup I should consider. That is a SIMO or multi. That is what you call what type of coding technique I should consider. All this would be decided at the base station. So, as we see that why CSI feedback matters is base station requires high quality CSI to perform, that is pre-coding, multi-user scheduling, and adaptive modulation or coding, which are essential for, that is massive MIMO performance. So what are the practical concerns in a real system? So as I said previously, the most commercial deployment presently operate in, that is frequency duplexing mode. Okay, so where uplink and downlink channels are not reciprocal in nature, whereas in TDD it is same. So hence CSI must be fed back explicitly from the UV. So as the massive MIMO scales to tens to hundreds of antenna, the dimension of the CSI matrix, which we are going to see later, grows rapidly and leading to substantial feedback overhead. Okay, so the core challenge is feeding back this entire CSI matrix becomes impractical and bandwidth inefficient. It becomes bandwidth inefficient for large antenna arrays. So these drives the need for what is called CSI compression or some sparse or low rank representation to get feed the CSI from the UV to the G node B, or learning based CSI feedback framework. So that is the motivation for that going for CSI feedback. So what are the conventional approaches which are used for solving these CSI? So what you'll see is the mainly they focus on reducing the feedback overhead by using a what is called spatial or temporal correlation of CSI. So first we should understand what is the difference between spatial and temporal correlation. So we know that spatial means we have many antennas. So the that is channel which is considered at one antenna, it may be same at other antenna. So you can consider the that is channel at one antenna to estimate the channel for other antenna. So that is what you call spatial correlation. Other is temporal correlation. So when a slow moving user consider the channel, there won't be that is drastic change in the channel condition. So that is what you see, that the channel at some particular time t and after t plus 1 it would be similar. Okay, so that is what you call temporal correlation. So some 2 days back we were discussing about age of time. So similar case here. So in that case we call it as temporal correlation of CSI. So they use these two concepts to reduce the feedback. Okay, so in case of correlated CSI, usually it can be transformed into what is called uncorrelated sparse vector in some bases. Like then they can use the what is called compressive sensing to obtain sufficiently accurate estimate of the sparse vector from the undetermined linear system. But the conventional compressive sensing techniques like TVL3, lasso, L1 solver, and then matching pursuit, and then OMP, they have been used in the literature. They have various limitations. Like selecting a suitable specifying basis is difficult to assure the high accuracy of reconstruction. The structure of the channel is not fully exploited, and encoding procedure is simple, but decoding procedure transforms into an optimization problem, and that demands a significant computational time and resource. And these schemes require multiple iteration, leading to what is called slow convergence. The existing 5G new radio system adopted what is called CSI feedback using codebook based methods such as type 1 and type 2 codebooks. When high accuracy in CSI is desired at the base station, as the size of the code becomes huge, the making the process practically infeasible, and it's also time consuming in nature. So this has made us to move towards some of the new approaches like deep learning based approaches. So deep learning for CSI feedback in 5G and 6G is as we see that there is a remarkable success of deep learning in domains such as image processing, natural language processing has accelerated its adoption also in wireless communication. Last almost decade, we are using that is deep learning in problems like solving the problems like adaptive modulation and signal identification, and then channel estimation, many more. So last December 2000, 3GPP release 18 initiated a study of AI native air interface with the three use cases. Like one is beam management, enhanced CSI feedback, and position accuracy improvement. So among them was one is enhanced CSI feedback. Mainly it was industry like Qualcomm which proposed this. Okay. So, and widely from that time onwards, so deep learning is used for this CSI feedback approach. So future 5G and system demands more accurate and predictive CSI to improve the downlink through throughput and reduce the uplink overhead. And with the support of 50 industry contributors, that is AI-enabled CSI feedback has been identified as a promising standardized use case. So existing, there is some deep learning based CSI feedback methods like CSINet, ACRNet, CRNet are and there are every that is recently lot of that is deep learning networks have been proposed. Okay, so coming to understanding about that CSI feedback, first we need to understand system model. So this system model is mostly many of the that is transactions which have been published. They consider this particular model, and we have also considered. So here we consider a single cell massive MIMO system operating in FDD for a downlink scenario. It pre-assumed that base station has NB transmit antennas and user equipment has NM receive antenna. But for simulation, initially we have considered NM is equal to 1. And multiplexing, which is considered is OFDM, employing some NC subcarrier. Then the received signal at the nth carrier is given by this particular equation. And here Xn is the transmit data symbol, Wn is a additive white noise with a nth subcarrier. Un is the pre-coding vector designed by the base station based on the received CSI. And other factor is the channel vector for a particular subcarrier. So therefore, you will see that the downlink CSI matrix, as I said, it is huge in nature. In a spatial frequency domain can be expressed by capital H, and which is the size of that is NC cross NB, where each column is a frequency domain channel vector and each row is a space domain channel vector. And the base can design the precoding vector UN once it receives the H that is fed back. And in FDD system, UV should return H to the base station through some feedback links. So you'll see that total number of feedback parameters, if no compression is performed, it is that is NC cross NB. And you'll see that it is assumed that CSI, in this case, we are not doing the estimation. We are considering that CSI is already present at the user equipment. Okay. And if you consider CSI estimation, then it would become a combined problem of estimation and feedback. So here we are considering only the that is feedback. So we assume that that is channel state information is already present. So what we will see is that due to the limited that is delay spread of wireless channel, the time delay among the multiple paths is within the limited period. Okay, so CSI matrix shows the what is called parasity in a delay domain. So you will see that if the number of transmit antenna is very large, that is NB goes to infinite, it is assumed that CSI matrix in angular domain can be derived from the spatial domain by performing what is called DFT, discrete Fourier transform. And also we can exploit what is called parasity. So that is from the main paper, okay, which has been taken. So you will see that CSI matrix is converted into what is called a spatial frequency domain into what is called angular delay domain by 2D DFT, and it is given by H tilde, where WA and WBH are the DFT matrix of the that is after 2D DFT operation, and they are square matrix of order NC and NB. So in case of delay domain, you will see that the first rows, that is NC tilde of the H contain values, because the time delay between the multipath arrival lies within a what is called some limited period. So you will see then we can retain only the first that is 32 non-zero rows and remove the remaining to get what is called NC cross NB truncated matrix. So as you can say, this is a free processing. So the number of real parameters of H tilde is now considering the real and imaginary part 2 into that is NC cross NB, which remains till the large number in massive MIMO reside. So here you will see the figure shows that is when you put the that is your channel into delay, that is delay domain. Okay, so where it becomes somewhat sparse in nature, and you can eliminate the that is non-significant terms. So by considering that, now still considering massive MIMO system, still it is a huge number. So it can be compressed into what's called k-dimensional, that is a vector, or what we call code word. That compression is defined as a data compression ratio, which is calculated as k by n. So n is that is 2 into NC tilde cross NB. So this is a fundamental. Okay. So the first paper who used that is particular concept. Okay, they use the autoencoder. So autoencoder, what it does is at the autoencoder part would be at the UV side. Okay, it compresses the that is channel matrix. Okay, and at the decoder side, and it is able to that is get back the original matrix, estimated matrix. Okay, so that is the first network which considered was CSI net. Okay, and here the problem, it was simple network. Okay, so the problem with this CSI net is it uses a convolution layer of singular size. Therefore, the proper future extraction could not be taken into account. So we propose what is called that is variational autoencoder based CSI feedback for massive MIMO system. And this variational autoencoder is a special type of autoencoder which employs what is called stochastic latent space, means compressed vector, which is generated is tractable distribution of typically Gaussian type. So where you will have your information in terms of mean and that is variance. So here it can represent the that is latent factor as a probabilistic distribution, and also model the model. It employs the convolution with different filter sizes at the encoder to extract the features and to improve the channel matrix reconstruction with a high compression ratio, which was this particular work was published in Wireless Personal Communications Pinjar. So this is a network which is given at the encoder side and decoder side. So we use at the decoder side a refined net, which is similar to that is the initial paper. So at the encoder size, you have 2D convolution at the first size with a 1x1 and batch normalization. Then you have what is called 2D 5 convolution network, then max pooling, then that is convolution network, then flatten, then we do the flattening, then using the dense network. Then at the decoder, you have a dense network. Then you reshape it into 32, 32, and 2. Then we have a refined network of this configuration. Then again, we get back the our original that is estimated channel. So here you see that the output of the encoder is called inference model, which is defined by this particular equation. So it describes the network with a that is parameters. The mean of the Gaussian distribution is represented by mu pi, and variance is represented by sigma. The latent representation, that is code word, okay, ZU, is the k-dimensional vector, and the decoder is called a generative model. The training model is done in end-to-end fashion to maximize the standard objective of variational encoder as shown here. So that's about the network. The experimental setup here for a fair comparison of the proposed network with others, we use what original data set provided by Wen and et al., which is given as a reference here. Here, data set which was used was COST 2100 channel model. And the channel matrix was generated for two scenarios, outdoor and rural scenario operating at 300 megahertz, and indoor picocellular scenario operating at a frequency of 5.3 gigahertz, and uniform linear array with the NB equal to 32 antennas employed and subcarrier of 1024 is used. This is a training parameter. 1 lakh training parameters are considered with validation data set of that is 30,000, testing 20,000. It was run for 1,000 FO, batch size of 200, learning rate of 0.001, and optimizer use was Adam optimizer, and last function was mean square error, and it was simulated in that is tensor keras with GPU backend. Here you will see, before going to the results, we need to understand performance matrix for CSI. So one is NMSE, other is a that is what you see is that correlation that is cosine similarity. So here you will see that the input given to the network is S tilde I. The combination of encoder and decoder has the corresponding set of parameters given as theta, which is encoder, which is a combination of encoder to that is decoder. The channel matrix that is reconstructed is defined as HR. The computation of loss function is given by L theta. And here you will see that the NMSE calculates the difference between the original channel matrix H tilde and the recovered channel matrix HR. So as the NMSE goes down, we say that our channel reconstructed is best one. And one more performance matrix is that is a quality of performance pre-coding is analyzed using what is called cosine similarity, which is given by this particular equation. That is a expectation of 1 by NC of summation of n equal to 1 to NC. Okay, HRN Hermitian of HN tilde that is norm divided by that is HRN norm to HN norm. So the reconstructed and original channel matrix of the n subcarrier is given by HRN and H tilde n respectively. So if the ratios of that is HRN and norm of that is considered as a beam forming vector, then HRN Hermitian and that is HN tilde HRN norm is the corresponding channel achieved at the UV side. So as the value of cosine similarity approaches 1, we can inform that the precoding performance is better. So when you compare our network, okay, because we considered now 2 parameters, okay, one is NMSE, other is the that is what is called that is cosine similarity parameters. So for different compression ratio, that is for different that is what we call compressing sensing networks, as well as techniques, as well as that is what we call CSI network, which were previously proposed, were compared with our variational autoencoder based approach, where you see that you have, when you compare, it has got a very low, is NMSC compared to other network. So in terms of that is what you call first one is with indoor scenario, other is with the outdoor scenario. So when you compare with the cosine similarity, it is the best. And this is a result for the case of original gray plot of original channel matrix compared to that is what is called reconstructed matrix at a compression ratio of 1/64. Still, it could get some of the information, channel information. So when you do the, that is what you call ablation study in terms of log, we see that the variational encoder was compared to the CSI net, it was having a higher plops, but compared to other networks which are proposed, okay, it was better. But because the first CSI net which was proposed, it was having only 2 layers, okay. So because of that, its reconstruction compared to our network, it was not as so better. But in terms of law, that is in computational in complexity. So that is about the, that is our first network. So to quickly, as our time is up, so quickly I will discuss about our next that is network, where it was published in the IEEE communication letter. The motivation of this work is to design a lightweight framework that shows satisfactory performance in diverse scenario and feasible to be deployed in real-time environment. So that we call it a low complexity deep learning framework for CSI feedback in massive MIMO system. So key contribution of this work is, so I will just only mention the key contribution and directly take to the results. So the evolution on practical 3GPP channels, most of the prior studies for CSI feedback using a deep learning, they use the cost 2100 data set, where they evaluated the proposed, here we have proposed the network called that is dilated convolution, that is channel reconstruction network. We are considering a NRCDL channel model, which is a 3GPP release 18 specification compatible model, whereas the cost 2100 they were LT compatible model in this NR cluster delay channel model, okay, which is synthetically generated by us using the MATLAB, and where you see that it also considered the is what we call massive MIMO configuration into it, and it also considered beam forming. Okay, all those steps were considered, and it was more reliable compared to that to define for 5G and 5G and behind, that is channel model. So we extended our work from MISO to MIMO. Most of the previous work were considered only the MIMO part. UV considering, they were considering one antenna. So then robustness under realistic impairments, the model real world non-linearities and interference and AVGN is added to the feedback forward, enabling the robustness analysis and quantization aware CSI feedback. So as you will see that when the channel matrix is given, it would be in terms of fractional. So we also imbibed what is called quantization here, and we studied that also, and lower computational complexity compared to the previous network, because we use what is called dilation, which use the similar type of inception network. And we considered the requirement as per the 3GPP release 18, and we generated mixed data set considering cost 2110 and NRC channel, and done the, that is performance analysis. So quickly going to the system model was similar, quickly going to the, that is result. So we compared with a similar type of that is network, and we saw that our that is network performed better in terms of compression ratio, as well as that is what you call cosine similarity. That is what you see. And also, as I said, we also considered when the code word is when it is moving through the channel from UV to the base station, it may be corrupted. So we added the that is AVGN noise and done the analysis for different SNR. Still, our network performed better. And also we said that the effect of quantizations were also analyzed for different compression ratio, and still we could get a better result. And comparing to the that is plop, that is ablation study, our network, we saw that it could have a that is same parameter as CR and CSNet, and plops were less compared to the that is previous that is networks. So, and we also analyze for the that is MIMO case. And last work that is what we call CBM variational encoder based CSI feedback for NRG complaint system. So here motivation was to design a novel network where attention mechanism along with a variational encoder was considered. And I'm quickly just showing the that is result because it's time up for the next speaker. So we see that our network, which is considered to be what is called convolution block attention model based network, which considered channel attention and special attention combination, and it could give the better result compared to the previous network in terms of that is what is called implementation complexity as well as the in terms of NMSE and correlation coefficient. So to conclude, you see that the CBM variation encoder based CSI feedback framework significantly improved the feature extraction, attention to the key propagation path, and CSI reconstruction accuracy. And it incorporated the channel and spatial attention and enabled the network to learn both what features and are important where they occur in the angular delay domain. And the model demonstrated the robustness to performance under AVGN impaired feedback and quantization mixed data set, aligning with the 3GPP release 18 requirement. And computational analysis shows that lower complexity compared to the CSI net and CR net and many of the networks, and making it suitable for future 5G and 6G deployment. And future directions include considering variety of broader NR channel models and going for joint channel estimation and feedback, and also considering using this CSI feedback for doing the what is called joint sensing and communication and localization, some of the important research directions which people are working on. So these are our references. Thank you. I am late by 5 minutes. If you have any query, let me know. So if you don't have any query, you can mail me also. We can add next that is speaker. Jai Prakash.
Sir, is it same link or he has another link?
No, same link, same link.
Same link, huh? Jens, I contacted him. Just wait, sir. Yeah, he is replying. I'm in the meet. Sir, he is in the meeting.
Okay. Just he can unmute and.
Sir, okay.
Doctor, I'm here. Just enable sharing, so please.
Yeah. Thank you.
Thank you, Doctor.
Okay. Dr. Ataya, I have made you presenter.
Screen is available, Doctor?
Yes. Dear participants, welcome to the third session of today's that is FTP. So we welcome Dr. Abdhamaldia Ataya. So we are honored to have him here. So briefly, I will introduce him. He's Associate Professor of Department of Electronics and Communication Engineering, Faculty of Engineering, Jagdig University, Egypt. And he is involved with EIS Data Science Lab, College of Computer Information Science, Prince Sultan University, Riyadh, Saudi Arabia. And he's a visiting fellow, Data Communication and Network Department of Faculty of Telecommunication Engineering, SUT University, St. Petersburg, Russia. He has done his bachelor's from Department of Electronics and Communication Engineering, Jagdig University, Egypt, and MSc in Electrical Engineering, Department of Electronics and Communication Engineering, Jagdig University, Egypt, and PhD in Electrical Engineering from Department of Communication Network and Data, St. Petersburg State University of Telecommunication, Russia. He is the author of more than 100 articles published in peer-reviewed journals, proceedings, well-known conferences, and member of editorial board and reviews of many high-ranked journals, reviewed more than 300 scientific articles, and guest editor of many special issues in high-ranked journals. And he worked as a that is program chair of 4th International Conference on Future Networks and Distributed Systems, organizer and programmer committee member of many international conferences. Then he participated in ITUT sector workshops and contributions, and in national and international research projects and grants. His research interests include 5G and 6G communication, unmanned aerial vehicle, Internet of Things, cloud computing, 5G, 6G use case and application, yes, software-defined networking, mathematical modeling of communication networks, teletraffic engineering, terahertz communication, vehicular communication, augmented and virtual realities, underwater communication, and signal processing and wireless communication and sensor network, so many more. So I request that is Professor Ataya to take the dais. We are very honored to have you on this particular session. Please, Dr. Ataya.
Thanks a lot, Doctor. Thank you so much. It's my pleasure to be with you. Thank you for you and for Dr. Jaya for this invitation. I'm sorry for the cam because my internet connection is somehow unstable. Friday in Saudi Arabia, the weekend, so I'm at home. This is the issue. I'm going to start with the integrated 6G communication. Our agenda, first I am going to introduce the way to 6G, the normal 6G, and then we are going to move to the integrated 6G networks and the main structure of the integrated 6G. This is a new paradigm that will come after the first release of the sixth generation. So we speak deeply in the future. Then we are going to speak about the virtualization and the network slicing for the integrated 6G. What are the main slicing layers? And then I will give you a brief introduction about the quality of experience and the quality of service related to the integrated 6G. Then, inshallah, I'm going to introduce some prototypes and some solutions produced in our labs and some of the research of the already published research works. We have some cooperation or big cooperation with the International Telecommunication Union related to the standardization sector. I'm going to introduce some of our contributions or our standards that already standardized through the ITU study groups and the possible ways for cooperation for your students. They can apply for such opportunities. First of all, I'm going to give you a brief historical description of or brief historical overview of the evolution of the network generations or the mobile generations, moving from 1G until the current 5th generation, and the future or the beyond 5G and moving to the 6G. We can split these generations into 4 main waves. The first wave, or the first let's say that this is the first wave of the mobile generations. We can consider the first generation and the second generation as the first wave of the mobile communications. Then the third generation and the fourth generation, we can consider them as the second wave. The fifth generation, separately, the new era of telecommunication, so we can consider it as the third wave of the mobile generations. And then the fourth wave is the upcoming 6G. Why we split them into such categories? Maybe the first and the second generation have many similarities. They only support voice calls and text messages. That's all. And moving to the third generation, or maybe not only the third generation, but the last releases of the second generation, and then the third generation and the fourth generation, we start a new era of the mobile internet. So the mobile generations, the third generation and the fourth generation, not only provide or not only support the audio transfer, but although they support the video transfer. Moving from the third generation to the fourth generation, the only thing that changed is the quality of the service improved. For example, if you try to make a video call through the third generation and then you try to make it through the fourth generation, you will find that the quality of the video call will be better in 4G and fourth generation. However, there are some limited features of the new generation, of the fourth generation, compared to the third generation. But totally, they do the same with improved quality. However, moving to the fifth generation, the ITU, or the International Telecommunication Union, announced new, and the 3GPP announced new services, and that's why we consider it as a third wave. This is a separate wave compared to the previous generations. The fifth generation is expected to introduce the same services. You can make an audio call, you can make a video call with improved quality. This is the same as the previous generations, but with improved quality. But it will allow new services, and this is the issue. I'm not speaking about the first commercial release of the fifth generation, but I speak about the beyond 5G, about the after 2 or 3 years, what's planned by the International Telecommunication Union. They speak about the sending the human sense instead of only sending the audio and video. We speak about the tactile internet. Tactile internet, this is a new era of telecommunication. You can send the human sense in real time, and this is a big advance. Maybe the fifth generation can handle this, or maybe they fail to achieve this. But anyway, if they can't achieve this over the fifth generation, it will be the main use case of the sixth generation. Moving to the sixth generation, we speak about new requirements, not only related to the the bit rate and the end-to-end latency, but there are many other requirements. We will speak in details, and there are many other new use cases and new applications that make this new era will be like a revolution in telecommunication. So why we need the sixth generation, or why the ITU and the 3GPP announced the sixth generation of mobile? We have, or they require new services. These services can't be supported by the existing mobile networks, mainly the up to the fourth generation and the first commercial release of the fifth generation. They can handle these services. Many you speak about the services that require an end-to-end latency of sub-millisecond. It can't be achieved by the current existing networks and the upcoming networks. So they need a new system that achieve such latency. If we can achieve such latency, we will provide new services. These services include the telepresence and the holographic communications. We will speak in details related to these use cases. However, to achieve this, there are many challenges. How we can achieve the, I speak about the 1 millisecond end-to-end latency, and this is one requirement. However, there are many other requirements related to the reliability and network availability and the network coverage. All these requirements are extreme requirements compared to the existing generations. So all these can be considered as the challenges. How we achieve these challenges? Speaking about the sub-millisecond latency, even the 1 millisecond latency for the first commercial release of the fifth generation, the end-to-end the achieved end-to-end latency is 10 milliseconds. So they need to, by the end of the fifth generation era, they need to reach to the 5 milliseconds to support the AR and VR applications, mainly for the online gaming. And this is a big challenge. How we can reduce this, or how we can have a network structure and network protocols that can reduce this 5 millisecond end-to-end latency to not only 1 millisecond but sub-milliseconds, so we can provide applications like the holographic communications or telepresence and so on. This is a big challenge, and mainly imagine that we transfer with the speed of light. So if you imagine that only we have I'm sending a data on the free space with light speed, so it can be transferred to the 300 kilometers. This is only for one direction. If you consider both, the signal will travel to the receiver, and then the receiver will acknowledge the transmitter. So you will consider both ways. So it means that the maximum distance only in 1 millisecond in order to send a signal from the transmitter to the receiver, and the receiver acknowledge the transmitter in 1 millisecond. All this happened in 1 millisecond, and I have only the delay related to the propagation delay only. The maximum distance between the transmitter and the receiver will be 150 kilometers. 150 kilometers. If you consider the delays in the transmitter and the compression and the communication protocols, all these delays, after you modify, or you will use the recent hardware or the recent protocols, the recent developed protocols, even the theoretical ones. Imagine after you exclude all these other delays with the propagation delay, so they reach the maximum distance between the transmitter and the receiver in order to achieve a communication within 1 millisecond. The maximum distance between the transmitter and the receiver will be 10 kilometers, and this is theoretically, not real. So how we can do this? We need to transmit a signal from place to another. It may be between two different countries. So how I can achieve an end-to-end latency over the 6G or over the payload 5G networks with 1 millisecond or with sub-millisecond? So this is a big challenge. So we need a new network structure. It's not only about the network structure. We speak about the propagation delay. The signal will travel with the speed of light, so it will be limited to the speed of light. So how we can overcome this? All these are challenges with the same 5G and with the 6G. The International Telecommunication Union announced a focusing group related to this, related to the 2030 networks. For ITU, they have an alternative name of the 5G and the 6G. For 5G, they have IMT 2020, and for 6G, they have IMT 2030. It is the same, but alternative name with the same requirements as announced for 5G and for 6G. But usually the 3GPP use the term 5G and 6G. However, the ITU usually use the IMT 2020 and 2030. So they announce a focusing group related to the specification of the 6G or the IMT 2030 and the network architecture that may achieve such requirements. All this theoretically, just a discussion. Such a focusing group. Under this umbrella, under this focusing group, we have many working study groups, mainly study group 13. They are working in this. They are working in developing standards that can achieve this. All the materials, most of the materials, I'm not saying that all, but most of the materials can be found in the website of the International Telecommunication Union. You can go there and you can download these standards. You will find a useful material. Based on the announced specification from the ITU, they announced that the 2030 networks should have the network structure that achieve these features. The network should be simple. The network should be deterministic, and the network should have a high level of resilience. Going through this, they announce these features and they discuss each features, and later they are going to work on each feature, how we can achieve this feature, what are the recommended technology when building a network structure for the 6th generation, what are the key technologies that can be used to achieve or to give these features. We will go in details later. Now I'm going to shift from the International Telecommunication Union to the other standardization group, which is the 3GPP. 3GPP, they have the term 5G and the term 6G. So how we can move from the 5th generation, because we already have the first commercial release, so how we can move from the 5th generation to, or what the roadmap between the 5th generation reaching to the 6th generation in 2030. They announced that first of all, we will have the first commercial release of the 5th generation, which is the 5G. Then we will move to a new era. They refer to this era as the short-term evolution of the 5th generation. Then we will have a medium-term evolution of the 5th generation, and then we will have the long-term evolution of the 5th generation. Each stage will have its own characteristics, and we will evolve, moving from the normal or the first release of the 5th generation to the short evolution 5G. We will evolve, but this evolution, or this part of the evolution, will support or will handle some of the announced requirements of the 5G. However, we need to evolve. We need to continue evolve until we reach to achieving all the announced requirements for the 5th generation only, and then we will move to the new era of the 6th generation. For each system, you will find the technical details in the 3GPP documents. For the first commercial release, you can find all details related to the network structure and the capabilities and the requirements and the key technologies in release 15 and release 16. Release 15 and release 16, published by the 3GPP until before 2020. For the short term, they are now working on this. We already passed. They passed this area. The short-term evolution. This is the second evolution of the 5th generation. they increase the number of the massive MIMO antenna, and they increase the number of the frequency, they increase the frequency range. You can get more details related to this in release 17 and release 18. Then we are now in the middle bottom. We are now in the medium term evolution of the 5th generation. All details related to this exist in release 19 and release 20, and about release 21. Release 21 will be available next year. So we speak about release 19 and release 20. About release 20 can be found on the 3GPP website. Then we will move to the long-term evolution. By the end of the long-term evolution, we will achieve all the announced requirements previously announced by the 3GPP. And these requirements are the same that announced by the ITU for their IMT 2020. After this will come the 6th generation. From now, they are working on 6th generation. The 3GPP, they announce the requirements, and if you get the release 20, you will find about dedicated with the 6G, but most of the document dedicated with the short-term evolution of the 5th generation. They announce key requirements or key technologies for the 6th generation. These aspects include that in order to achieve the requirements, I'm going to speak about these requirements in terms of the coverage and in terms of the network availability and in terms of reliability. In order to achieve these extreme requirements, we need to have new technologies and new network architecture. About of this is to apply the paradigm of the 3D networks. All network will be based on the network virtualization concept, and the cell heterogeneity should be achieved in more easier way than what happened in the 5th generation. They speak about each part of these in details. We will go through some of these key technologies later. For networking, they have 3 main concepts now. They have the concept of the nano network. They use molecular communication in certain way they use graphene to achieve what's called the molecular communication. They use it in the physical layer to reduce latency. From the nano network come a new paradigm, what's called the nano IoT. Now they have bio networking. This is another paradigm. All these they try to achieve a part of the announced requirements. However, each umbrella of this key technologies is away. This is a new direction. You can go through this direction. You will find many available publications. Even in this direction, you will find many directions, many sub directions in each direction. So you need to just to have an overview of the 6G umbrella, and then you need to select. Maybe first of all, you need to select which layer to go through, and then if you select the physical layer, you will find many things in the physical layer. You need to go through the physical layer to have an overview of the 6G physical layer, and then you can go. All this theoretically, still there's no standardization related to this. Another thing, the optical networking and 3D networking. Optical networking, now they speak about the concept of the fiber wireless communications. So this is a new paradigm to link the wireless and the fiber communication in a certain way to achieve the reliability requirements and latency requirements. And they speak now about the 3D networking, mainly this term related to the achieving the integrated 6G or supporting the integrated 6G network. We will go to after 2 or 3 slides. We will go to the integrated network, the integrated 6G network, and what they intend by this concept. Speaking about the requirements of the 6th generation, I'm going to go through some of the key requirements, not all key requirements, but these are the most important. Speaking about the latency, 6G services will require an end-to-end latency of sub-millisecond, and this is a big challenge. We have two curves. The red one mapped to the 5G, the announced end-to-end latency, or the announced requirements of the related to the end-to-end latency in the first generation is it should be 1 millisecond. However, most of the research work and most of the even for the ITU and 3GPP technical reports now speak about reaching to the 5 milliseconds, and it will be enough. They will shift some of the use cases that require 1 millisecond to the 6G era. In 6G, we need to go beyond the 1 millisecond. Speaking about the mobility, we need to increase the mobility. The first generation, it will support high mobility, but this high mobility, it will be enough for someone who's speaking in a train. It's okay to have a good coverage and to have a good connection there. However, someone who speak who had a higher mobility than this, who's speaking in an object which is moving with high mobility than this, it can't be covered by the fifth generation. However, in the sixth generation, we speak about the mobility that may reach to up to 1,000 kilometers per hour, and this extreme high mobility. We speak about the data rate. In data rate in the sixth generation, we need to reach up to 1 terahertz per second. In the fifth generation, we speak about the 10 gigabit per second. Imagine that you can download something from the internet that relate to 10. I'm speaking about the fifth generation, 10 gigabit per second, 10 gigabit in 1 second. This is it will be hard to achieve this. Still, now in the fifth generation, they reach it to, for the first commercial release, they reach to 1 gigabit per second, and this is they are limited to the hardware. When you download the 10 gigabit in 1 second, you need hardware that can go with this. So it's hard to find the hardware that go with this. So there are many limitations in this part. However, they are working on this. Now they have the photonic devices, the photonic processes, and they speak about the quantum computers and all these. So we are waiting in this way. However, now we speak from the network point of view, how to achieve data rate up to terabit per second. This will be happen related to this challenge. We can achieve it related to the spectrum. Which spectrum should we use to achieve this? Which protocols will be used? And the spectrum, the frequency spectrum control about of these. So these are some KPIs, or the key performance indicators related to the 5G and related to the 6G and 5G. What are these for some applications? For example, when we speak about the augmented reality and the virtual reality, what are the key performance indicators in the fifth generation? However, when we move to the sixth generation, these requirements will change, and we will have the advanced services of the AR and VR. You will have the telepresence. The same for the e-health and the Industry 4. We have the Industry 4, and then now they speak about the Industry 5 and 6G. The same. They have a paradigm called the Healthcare 4 in the fifth generation, and they speak about the Healthcare 5 that maps to in the same way to the Industry 5. These are some I listed some of the key performance indicators in this table compared between the fifth generation and the sixth generation. Even some of the key performance indicators of the fifth generation are not available in the current existing fifth generation. However, they aim to reach to these key performance indicators. Now we reach to the integrated 6G. In the integrated 6G, we need to integrate all communication tiers in a single platform. Speaking about the IMT 2030 or the 6G, we speak about the network, the terrestrial network. We speak about the ground network. However, there's no integrated framework. So ITU ITU announces the integrated 6G. Integrated 6G, it will be an alternative, or it will be beyond the 6G network. How we can integrate all communication tiers in a single platform. How we can integrate the ground and the space and the air, the water communications all in a single platform. So every place in the integrated 6G network, every place will have a coverage. Every place will have a coverage, and it can be connected to every place. Every place can be connected to every place. The water tire can communicate with the space tire. The space tire can communicate with the ground tire, all in a single platform, all through one operator or integrated operators. All this will be over the integrated 6G network. This is the concept of this term. In this, we have many layers. We have many tires, as we see that we have the ground tire or the terrestrial layer, our terrestrial tire. We have the space tire. We have the air tire. We have the sea tire. For the ground tire, as we see in the right part, it will cover the ground network with all applications, all announced applications for the 6G. There's no new services related to I'm comparing the integrated 6G with the 6G. All the announced use cases and applications for the 6G will be the same for the integrated 6G. For the space, we will have many layers. It depends. These layers depend on the altitude. Some particles will be on the low altitude, and then some of the unmanned rail vehicles or airplanes and these will be at the medium altitude, and some will be at high altitude. We speak about the satellites, and we speak about the satellite at the low Earth orbit satellites, and then move to the geo orbit, and then move to the satellites that exist in the deep space. We categorize them into these 5 layers. However, this is from our side. You can have your own. This is just a recommendation. So how we can integrate in the integrated 6G, how we can make this integration, how we can integrate all the communication tile, all these communication links. We have as we see in this slide, we have many communication links, heterogeneous communication links. How we can handle all these communication links? What I mean that one of these communication links may carry data. I need to move or transfer such data on another communication link. So how we can go through this? So we need to have a network structure, a protocol stack that can achieve this. Here list the main tires. We speak about the space tire and the air tire and the ground tire and the water and underwater tire. All this should be over one platform. The integrated 6G should have the same applications as the 6G. These applications include the Industry 5, autonomous vehicles, and Healthcare 5, the extended reality, including the telepresence, and the all unmanned rail vehicle applications, including military and civilian applications. And a part of these are the unmanned rail vehicles applications related to the network. Unmanned rail vehicles can have applications that support the network. For example, they can provide coverage for some places. They can assist the network when the network capacity are out. They can provide or they can support the ground-based station in certain way. There are many research in this. They can provide the wireless charging for some devices, for example, IoT devices. This is another part. Another application related to the brain-computer interface applications, and the applications related to the smart city applications. And the other main important thing is the holographic applications. Now they speak about the holographic type communications. This is a new era of communication paradigm. We have the machine-to-machine communication. We have human-to-machine communication, human-to-human communication. Now they speak about the holographic type communication. We will move to a new era. Holographic type communication, it's a kind of moving the hologram in real time, moving your holograms in real time with the human. I will merge this with the tactile internet. Tactile internet, you need to transfer. Tactile internet announced it as one of the main use cases of the fifth generation, but now they speak that not mostly they will shift it to the sixth generation because the tactile internet needs an end-to-end latency of sub-millisecond, and it's very hard to achieve this now with the proposed structure. And even if it's evolved, it will be hard for them to achieve this. In this, you will transfer the human sense. Imagine that I think all of us know about the devices with high degree of freedom, so it can extract the human sense and it can give you the human sense. It's okay for these devices. Now the hardware already exists. However, the only issue is how to transfer this. How I can extract the human sense, but how to transfer the human sense in real time? It is somehow complicated because you need to transfer the human sense in 1 millisecond before if the delay of the end-to-end latency exceeds the 1 millisecond, it means that the human sense will be interfered, and you will lose some of the human sense. For example, if you use your human sense to control a remote robot, you will use a part of this control if the delay exceeds the 1 millisecond. Here we speak about the use case and applications in details. I'm going to skip this. These are the use cases. Mainly here we dedicated with the robot application in the era of the integrated 6G. What I mean by the robot, all unmanned devices. Here the robots are used in the in e-learning and in learning and telesurgery. Robots can be used in the healthcare 5 for diagnosis. You can find many applications related to robots. Mostly we speak about replacing the human with this, so that's why we are interested in such thing. Then I'm going to move to give a general structure of the integrated 6G network. We can see this the whole structure of the integrated 6G, even whatever the tire was, at 3 main parts: the terminal part and the radio access network and the core network, the same as in 5G and the same as in 6G. They split the network structure into 3 main parts: the terminal part or the physical part, and the radio access network and the core network. When we apply the concept of the network slicing, you split the network, you divide the network into parts. Each part of the network can handle certain service. For example, if we need to handle or to provide the mobile broadband services, so I'm going to take all the devices, all the terminal devices dedicated to the enhanced mobile broadband services with a part of the radio access network. This part will be dedicated only for the enhanced mobile broadband services and a part of the core network. So this layer or this part of the network, it will be acted as a separate network. However, it's a part of the main network. This separate network will work to provide this service. So what's the benefit of such paradigm? What's the benefit of the network slicing? Split the network into slices. For example, enhanced mobile broadband services now require network resources with certain usage. After a short time, there's no enhanced mobile broadband services, so I have available resources for this. So I can take these resources and I can give all these resources to another slice and I can use it. So you can manage the network resources dynamically, and this will be good for in terms of the network resources. Here the same, we split the network into a business layer or the application layer and the service layer and the infrastructure layer. This is another structure, but mainly the first structure or the previous structure, this one can help the people who build the network structure, and this one who only for the people who are working with the network virtualization, who will build the network functions or the virtual network functions and the network orchestrations and these. So we build the structure for them. This is a brief description of these layers. Now we reach to the quality of service and the quality of experience and the quality of customer. The common term, the quality of service. This is very common until we reach to the fourth generation. We have only the only term, the quality of service. Until now, with the first commercial release of the fifth generation, the most common term is the quality of service, and you can say that the quality of service is good or bad, or you can control this based on some parameters. They are the same in the previous generations. In the fifth generation, you can find a list of them with KPIs, with announced KPIs, with the ITU and 3GPP, and it's okay for this. However, moving to the beyond 5G and to the 6G, now they ignore the quality of service, and they focus mainly on the quality of experience and the quality of customer. Quality of experience is very important, mainly for the telepresence application, telesurgery, all applications in which there is a human interaction with a machine or human interaction with other devices. So we speak about the quality of experience. There's a big difference between both. Quality of experience have more items. So you should monitor all these items to judge the quality of experience. I think in the previous release of the 3GPP, they have complete details related to the quality of experience of the 6G. You can find this. It will differ from one application to another. You can find all details related to this in the technical reports of the ITU and the 3GPP. This is a small distinction between the quality of service and the quality of experience. The quality of customer, the quality of customer and the quality of experience. How to judge between both for a system. To give a brief for this, or to discuss this in details, we need to have a certain application. When I reach to the prototypes, I can go through this slide again. Here we give some description related to the modular architecture of the network. We divide the network into two modules. These are the common modules, the common network modules. But when we move to the physical module or the physical interaction, we will have the communication module. So the communication module, which communication interface will you deploy? Network will support. All communication interfaces can be supported. So how you can support this heterogeneity? The other part or the other module, we will go to the network or the core network. The core network we will deploy, for example, the software-defined networking. So we will have the OpenV switches or the OpenFlow switches or whatever the switches that support the SDN paradigm. We will deploy in the core network, deploy the concept of the microservice and the service migration. So we will have containers. We will need the virtual machine to be deployed. So this is the network modules. And for the control modules, in order to control the quality of service and the quality of experience of the network, how you can manage this. These are the modular architecture of the integrated 6G. I'm going to give a brief description of one of the key technologies of the integrated 6G. Indeed, this technology used in the fifth generation, and it will be used in the beyond fifth generation. It's the distributed edge computing. Mainly two main technologies will be deployed on. These are the base. of the 5th generation and the 6th generation. They are the distributed edge computing and the software-defined networking. And based on these two technologies comes other technologies like the network slicing, the virtualizations, and the intelligent network. Intelligent network, how we will use the AI at the core and at the edge of the network to achieve the network requirements, even for the 5G and for the 6G. Let's go through this video and then we will discuss this.
Dr. Atay, I think there is no audio, I believe.
What, doctor?
Audio. We are unable to hear the audio of the video.
Okay, so I'm going to skip and I can share with you.
Okay.
Okay, doctor. Okay. The video dedicated to the distributed edge computing, or what we call the mobile edge computing or multiple X edge computing. Both are alternative concepts. They use the multiple X edge computing or the mobile X edge computing in an alternative way based on the network. Another common term for the MIC or for the distributed edge computing is the fog computing. I think most of us already use this paradigm, or maybe use a hardware as a fog node. If you have a small project related to the Internet of Things, you will use the fog node. So this is a very common part for us. But how we will use this in the embedded 5G and in the 6th generation and the integrated 6G networks, how will use the MIC? First of all, it will give us many benefits. The distributed edge computing will give us many benefits. The first, it will reduce the end-to-end latency. How this will be happened? Now we speak about the communication delay between this MIC device. If we assume that we connect this MIC device, this is a kind of server. This is a cloud. If we connect this cloud to the base station, so when the end user communicate with the base station, so only one communication hub between the end user and the base station. So only one communication hub between the user and the cloud server. So instead of going through the core network and going to the remote cloud, now you go directly to the cloud service or the cloud server with one communication hub. So you reduce the communication distance between the cloud server and the end user, and thus you reduce the latency. MIC can increase the network availability and the network flexibility. Although network security, you can implement security protocols on the MIC server, so you can increase the network security. It provides a path for data offloading. It reduces the network congestion because using the MIC, less traffic will pass to the core network, and thus you reduce the overload on the core network. You can use MIC to manage the spectrum in an intelligent way. You know that MIC cloud or MIC server can implement AI and machine learning algorithms in certain way that can manage the network spectrum. So you can optimize the network spectrum using a MIC. So these MIC servers or these distributed computing nodes, which place we will put these clouds in which place of the network? What's the best place to put a MIC server on the network? One place, it is easy to connect the MIC server to the base station. So each base station will have, or each EMP will have a MIC server. So it is easy, but it will be costly for the network if you connect each base station with a MIC server, and there's no need for this. So it means that you will lose money for this. So searching for the best place for the MIC servers, we have many places, and it will depend on the network. Now they use a MIC server with the 4G, with the 3G and 4G applications, or 3G networks. 3G mainly for 4G networks. They connect the MIC server with the radio network controller. This is the best place to put this for the 3G, and for the first release of the 4G. Speaking about the LTE Advanced, they connect the MIC server to the macro base stations, and this is the best place based on the published research that analyze this. For the 5G and the 6G, and this is the most important, MIC server will be deployed, will be connected to the each base station. Not only this, but you can use the MIC server separately to provide computing resources who need it. For example, you can use the flying edge nodes. For example, you can have a drone. This drone can carry a MIC server only to provide computing resources to certain devices in a certain place. This is one of our established work in the distributed edge computing. We proposed a multi-level structure for a multi-level mix structure for the tactile internet mainly, and we can move it to the integrated 6G. We modified it to the integrated. We already modified it to the integrated 6G. I'm going to discuss it. This work is standardized by the International Telecommunication Union (ITUT) study group 13. This heterogeneous network, or this heterogeneous MIC system, deploys mainly three kind of the clouds, or three kind of cloud service. I say that each base station should be connected to a MIC server. So I will connect each base station with a small cloud server. We call it the micro cloud, or micro MIC. This micro MIC will be connected to each base station. However, for some base stations, I'm going to connect to provide a high capability MIC server. We call it a macro, a mini cloud. So we have a micro cloud, and we have a mini cloud, and we have a main cloud. This is our hierarchy. The micro cloud small server with small capabilities. It can provide some computing resources, but it is limited in terms of hardware, so its cost not high, and it can provide the required computing resources up to a certain level. Each group of the micro clouds are connected to a mini cloud. These mini clouds are connected to some base station. However, these base station require in their cells require high computing resources. So I give them high computing resources. I paid, or the cost is high in such case, but I will receive services in good cost. And all these mini clouds are connected to a main cloud. Only one main cloud located at the core network, so it can control all mini clouds. This hierarchy, we tested this hierarchy for heterogeneous services in terms of many performance metrics, and we record this. We have many publications related to this, and we standardize this with the ITUT in the study group 13. We modified this structure to the integrated 6G network. we try to use the same hierarchy, but we extend this hierarchy to cover mainly. We are dedicated with the ground. We move this hierarchy to the space. We have a layer, a new layer related to the flying edge nodes. We have some drones. These drones will be powered by some mix servers. These mix servers are heterogeneous as well. Some of them are fog nodes. Fog nodes, we consider fog nodes as a micro servers. So our micro MIC. So some of them are micro and some of them are mini. This for the air. We deployed this at different levels, and we tested this for some applications and for different metrics. This is our platform in ES Lab, and in cooperation with the 6G MegaNet Lab, we have this platform, and we are working on it long time. We say that the AI and machine learning will be deployed. I discussed the edge computing or the distributed MIC mainly for this. MIC has many benefits. However, to get all the benefits of the MIC, you should make it intelligent. They call it the intelligent edge. So how to turn the normal edge or normal MIC, or even the with our hierarchy, or even the traditional MIC structure, how to turn it to an intelligent, and why to turn it to an intelligent. I'm going to turn it to intelligent to achieve certain function. Maybe I implement an AI algorithm on this edge server to provide certain function to the network, or to optimize certain function from the network functions, so I get benefit for this. So one of these is that, for example, the live migration, how to migrate a task from one server to another. You can make this so a normal algorithm, or you can use the AI and machine learning to optimize the migration process. Now we speak about the microservices. You can do the microservices at the network edge in normal way, or you have your own protocol, or you can use AI to optimize this protocol to make this. When we discussed that we have a limitation due to the light speed, we are limited with the light speed. So how we can achieve the sub-millisecond? To overcome this, now they speak about, it's not now, I think this is more than 5 years they are searching on this. They are speaking about the something called the model mediated. Model mediated, it is a model based on the AI and machine learning. This model is built on the network edge. And for example, I need to control a remote environment. So I'm going to build a virtual model for the remote environment on the network edge. And I will interact with this virtual. I will interact with this virtual model, with the model mediated on the network edge. And the real interaction will be transferred. It's okay, it will take some time, but I will, for example, now I'm going to control a robot. So I will control this robot, so the virtual robot on the edge. And the actual robot will receive the actual interaction, but it will take some time. It will exceed this 1 millisecond. But in real, I'm interacting with the virtual, and the virtual expect, for example, the virtual replica expect that we have virtual replica at the other side. For example, I have an edge, a MIC server. This MIC server near to the end user, and another MIC server near to the remote environment. So the remote environment interact with the MIC server, with the virtual model, or the model mediated on the remote server, and I am at the end user. I'm interacting with the virtual model, or the model mediated, near to me at the network edge, and both virtual models at the two MIC interact in real. For example, the real interaction transferred from the network edge A to the network edge B, it will take some time. However, the AI will expect that my interaction will be like this. So it will give the interaction to the real environment before the real interaction come. So I reduce the end-to-end latency in such a case, and it will improve itself until reaching a high accuracy. So this is the brief introduction about the model mediate. So they will use this model mediate. This is a part of the application of the AI and machine learning on the edge server or the intelligent edge. They use the model mediate to reduce the end-to-end latency between the transmitter and the receiver. We have these segments in our lab, each of them related to a part of the network or related to an application, and we are working in. We have a group dedicated to this. We have a group dedicated to the robotic network infrastructure. We built a network infrastructure that can handle the robot applications. Another group dedicated with the holographic type communication and telepresence. Another group working on the distributed edge and the structure and the implementing applications over the distributed edge. And these are our segments. I'm going to share with you after we finish. If anyone is interested in cooperation in a part of our work, we can give him a brief description and brief details related to what we achieved in that segment, and we can cooperate. We are open to this. These are main research directions. We are working, this is from the application level, we are working with the high-dense IoT networks, and we are working with the swarm unmanned rail vehicles and how we can use it to support the dense IoT systems. We are working with holographic type communication and robot avatar. We are working with the ultra-reliable low latency communication, and we have a main group who is working on the network softwareization, mainly over the software-defined networking. I'm going to give quick overview of some of our prototypes. This is one of our prototype. Here, it looks simple, and I think it's available, but the new here is that the end-to-end latency. Now we in this prototype, this is a part of the tactile internet, but we achieved it in vicinity. For example, the transmitter and the receiver, the human hand and the arm robot, they are near to each other, so the signal transmitted for small distance. So there's no issue in this. So we can achieve the sub-millisecond in this. But in real time, in real situation, we need to achieve this real-time interaction. The same what happened with the end-to-end latency like this, but the distance between the human hand or the transmitter and the arm robot, the receiver, should be greater than maybe one in a certain country and the other, and the receiver in another country. For example, we may have a doctor our surgeon, who make a telesurgery. So how we can achieve this? This is the issue. So we achieved this. We achieved a sub-millisecond. However, this sub-millisecond we didn't go beyond the light limitations. This is another prototype related to the holographic type communication. We built our hologram, and first of all, this is the first challenge to build this hologram, and then we try to transfer this hologram within the same campus indoor, and within the same campus we already get achieve this type of communication or this transfer. However, we achieve this with the announced requirements, but with the distance between the transmitter and the receiver, the distance was 100 meter, and this is a small distance. We need to extend this, and this is a challenge. We published our work. We have an authored book, a recently published author book related to this. The whole book dedicated with holographic type communication. Again, we call our test bed. The third prototype, we have a telepresence suit. I'm going to share with you this. This telepresence suit it can receive and transfer the human sense in real time. I'm going to share this. This is another prototype related to the industry, the industrial 5 or industrial IoT. These robots, we got these robots, but we connect these robots to our developed Raspberry Pi based kits in order to make a synchronization in their operations remotely. So they receive the orders remotely. And they do this in a harmonic way. And we have application related to this. This is another prototype. I'm not going in details. I'm going to discuss some of our research activities. I'm going through this because publications are available online. Anyone can go through this and we can find the details related to this. All this related to the mentioned segments. So you can go and you can find. I'm going to share with you the presentation, and you can check this. Mainly, I'm going to stop here. This is a very important part related to the model mediation, the one I just discussed. This is an open and hot area of research. Anyone who is interested in the edge intelligence and how to deploy the AI for building a model mediator at the edge of the network can cooperate with us in this. We are extending our work in this. Finally, we have a big cooperation with the ITU. I think the second or the third slide we discuss the focusing group related to the 2030 networks. There are many focusing group announced by the International Telecommunication Union related to the 6G. Many of them are open to receive contributions and standards. And if you have a new idea, new protocol, you can just submit to one of the study groups, and they will discuss this, and they can turn this finally to a standard that can be used by other. This one of our this contribution, or the technical specification standard, one of our standards published recently related to the autonomous networks. Another open way that I need to discuss with you, the AI for good. AI for good is a challenge announced by the International Telecommunication Union. It is very useful for students at different levels till the PhD. You can participate if you have any idea related to how deploying the AI and machine learning for 5G and even for the 6G. We have an open challenge announced by our lab recently. We can share with you and you can contribute. This is another challenge announced by how to build an Ethernet into for the 6th generation. You can find all the details related to this challenge on the ITU link, or even on you can register on the GitHub link. ITU, if you need to participate in this, ITU will give you a free GPU access and notebooks and Python IDE, all this for free. And you can finally, if you win this challenge, you will get many other benefits. Thank you for your time, and I'm open for any questions. If you need to cooperate related to any field of our working area, just send me. I'm available. Thank you.
Dear participants, if you have questions to Dr. Ateya, please. It's a very interesting lecture where you could connect the network and how the body network and sensing practically, which has been demonstrated by him.
All this not demonstrated by me. This demonstrated by this is a big team. These are 3 labs are working together, dedicated with the test bed. So
okay.
No one can work in all these, but these are.
Participants, if you have any questions, you can unmute yourself. There is a
Hello, sir.
yeah.
Hello. Sir, what is the future of that edge computing, sir?
Dr. Ateya, you can you
I
answer
couldn't
the
hear.
question?
Please, can you repeat, doctor? I couldn't hear that voice. It wasn't clear.
What is the future of edge computing?
Edge computing, yes, sir.
Great, doctor, great. The future related, all the future of the edge computing, mainly related to the edge intelligence, how to both the AI and machine learning algorithms, and how to implement these algorithms for the edge. And because you know that 10 years ago they have been working on edge computing, but now they move to the intelligent edge. So and then, for example, if we speak about the Internet of Things application, so we need lightweight protocols. So how to develop a lightweight AI protocols that can be implemented for IoT. So I think this is the main direction.
Okay, sir. Thank you, sir. Thank you so much, sir.
There is a one question asking, like, is it possible to create a similar lab at our place? We want to have similar infrastructure.
Yeah, sure. We are free to cooperate. We can give you brief introduction related to our past steps, and you can go. It's very easy to go. Just have a team who is working, who is dedicated with the 6G, and you can start working as wide as you can relate to the main segments. for example, if you have a group related to the physical layer, another related to the network layer. So if you extend this, or if you have this, so you can start building. Speaking about the hardware, it depends on you. It depends on you. You can find a funder who can give you, who can provide you, or if the university have the ability, the funding availability to support this, it will be good. But practically, it's okay.
I think no more questions, I believe. Please share a contact to reach out to you. There is a
Okay, Doctor.
Dr. Ataya.
Okay, I'm going to share. This is my mail, and you can. This is my WhatsApp.
So can we put it in chat box? So
yeah, it's okay. It's okay. So.
dear participants, do you have any other questions?
It seems no more, Doctor.
Yeah, no more questions.
Thank you, Doctor, for your invitation, and I
Dr.
was happy to be with you.
Ataya, we are very honored and thank you for a very nice lecture and presentation. It covered a lot of things with respect to network, which previously that was not covered. Thank you very much.
Thank you, Doctor. Thank you. Thank you.
Yeah, thank you. Thank you. And good night.
Good night, Doctor.